Hi, I'm Jung Hee Kim, and I'll be presenting the differentiable HDR image synthesis using multi-exposure images. This is the joint work with Jung Hee from Naval Labs and our advisor, Seok Kang. High dynamic range images convey more information and are more robust to environment changes, such as illumination. Therefore, the high dynamic range imaging has been important for many computer vision applications, such as photography, displays, and also the autonomous driving. So to create HDR images, commonly used conventional approaches fused an image stack which were captured with different exposures. However, the method requires scene to be static, therefore there exists some infeasibility in constructing the stack in certain environments. For that reason, various deep learning-based methods were proposed to only use a single low dynamic range image to reconstruct high dynamic range image. Even with the recent approaches, there still exist some challenges in recovering the details of underexposed and overexposed regions of the HDR image. So we focus on compensating the existing challenges of using deep learning-based method. Deep learning-based HDR reconstruction method can be divided into two categories, which are direct method and multi-exposure stack-based method. Direct method generates high dynamic range image directly by feeding the LDR image to the network. As the LDR image has 8 bits per pixel and common HDR images have 32 bits per pixel, the ambiguity is large for the deep neural network to be trained ordinarily. Therefore, a large amount of LDR HDR image pair data is required. To compensate dataset quantity challenge, recent approaches utilized images crawled and collected from the internet, or the virtually constructed images. However, as the collected images have diverse dynamic range, the range normalization and the standardization process become ambiguous. Moreover, the gap between the virtual images and the real images might result in the network to be trained in the wrong direction. The multi-exposure stack-based method focuses on reconstructing the multi-exposure stack to utilize standard HDR image formation pipeline, which merges multi-exposure stack by using the portion of the images that are properly exposed. Previous method recursively generated relative up and down exposure images to accurately construct multi-exposure stack. However, as can be seen in the tone map result, severe local inversion artifacts occurs. The main reason for this drawback is that the network was trained only with the multi-exposure stack, which is not the optimal target of the method. Due to the limitations of non-differentiable radiometric calibration process in deep learning-based method, multi-exposure stack-based method had limitations in learning the whole HDRI process. In addition, as the method only focused on generating the relative exposure images, the connectivity between recursively generated images were not imposed. And moreover, the quality of generated images will rapidly decrease with the number of recursions, which result in missing details and local artifacts in the over and underexposed areas of multi-recursion images. To mitigate aforementioned problems, we propose a novel framework that performs both multi-exposure stack generation and the HDR image synthesis process. We propose a recurrent generator network to enhance the connectivity between recursively generated images by adaptively responding to the recursion numbers. We also applied image decomposition approach to disentangle difficulties in multi-exposure stack generation process. Lastly, we propose the differentiable HDR synthesis process, which allows multi-exposure stack-based method to be trained with the direct supervision of the HDR image. Our differentiable HDR synthesis layer first estimates the discrete inverse camera response function using the Delbecq and Malik's method. Delbecq and Malik's method fuses samples of multi-exposure images and estimates the function that minimizes the objective function, where E denotes exposure, the EV denotes exposure values, and G denotes the inverse CRF. As the inverse CRF has the form of the non-differentiable discrete function, the backpropagation of the function is limited. Therefore, we piecewise linearize the function to be differentiable and to enable the end-to-end training process for deep neural network. This layer imposes pixel-wise relation on multi-exposure stack during the training process. And for our proposed network, we have incorporated two-pathway approach to mitigate the difficulties in the recursive exposure transfer task. We use global network to predict and match global tone of the target image, while local network to predict the gradient-based local structure of the target image. We later fuse the two components using the refinement network. We use convolutional GRU layer in the bottleneck of unit structure for both global and local network to focus on the recurrent process and to adaptively respond to the recursion state by using hidden vectors. The global network focuses on matching the global tone of the relative exposure image, which is the histogram. We use following laws to train the global network. Here, capital A indicates the total number of exposures, and capital N the total number of pixels. The capital L denotes the number of pins in histogram, and CNT function denotes the function to transform image into the histogram. The local network focuses on generating relative exposure edge map, which were extracted with the Kenny edge detector. We train the network with the stated loss function. Here, the edge function indicates Kenny edge detection. Finally, refinement network focuses on combining the outputs from both global and local networks. We compute the L1 loss between multi-exposure stacks while imposing tone-mapped HDR loss between HDR images. We further utilize the contextual bilateral loss to reduce the effect of any misalignment between images in the stack. Here, H indicates synthesized HDR image and D indicates distance function between features extracted from bridges network. We have verified the effectiveness of the image decomposition method on both recurrent up and recurrent down generator. The local network guides the refinement network to make the details and contrast of generated images very similar to those of the target images, which global network cannot fully perform. For the recurrent up generator, the local network guides the final result to eliminate abundant details to match the target image, as can be seen in the edge map comparison result. The similar result can be found with the recurrent down generator. The results show that the image decomposition approach disentangles the difficulties of exposure transfer task. For experimental setup, we use VDS dataset, which has 48 scenes for training and another 48 scenes for testing. We further evaluated our method with the HDRI dataset, which has 50 different scenes, and weighs 1K dataset, which is 1,000 different scenes. We further use HDR BDP2 score to perform HDR quality assessment in PSNR, SSIM, and MSSSIM for the multi-exposure stack generation result. Comparison results for the HDR quality assessment were performed on both multi-exposure stack-based method and the direct method. Our method outperforms all the other methods on 3 different datasets with the HDR BDP2 score. The qualitative results show that our method recovers more details in overexposed areas and underexposed areas without any local inversion artifacts. We also conducted multi-exposure stack reconstruction comparison with the previous method. We verified that our method reaches similar performance compared to the previous method as shown with the quantitative result. However, our method outperforms in the HDR quality assessment and does not generate any local inversion artifacts. As a result, our method reaches high performance on both multi-exposure stack reconstruction and HDR image reconstruction. For more detailed results, please see our paper and supplementary material. Thank you for listening.
Okay, so I've got all the authors here, and I also have a bunch of questions. I'll just call out on the author and ask them questions, and they could respond. In addition to this, there'll there may also be questions on Rocket Chat, which I'd encourage you to respond to right after this live Q&A. So the first question for 5, Flo, is in your simulation control slide, you introduce a predictor network. And how do you prevent this observation predictor network from selecting trivial states as solutions?
Okay, we use this predictor network to kind of allow the network to look further into the future, and we pre-train this with actual simulation data. So we simulate reference data, and on that data we can train the prediction network already, and then reuse this in the optimal control. And so you can just do a normal supervised loss for matching physical states there.
That's good. So we have a question for Paula on DeLuca. To what extent are these simulations differentiable? For example, do we get gradients with respect to all plausible contacts and stuff?
So for now, we do have more simplistic forms of environment. So most of our state progression, or the state progression can be modeled to a differentiable function. So you can take most straightforwardly derivatives through that.
Okay.
Yeah, you will get the Jacobian, and so you'll have a derivative with respect to the state and the action at any time step.
Sounds good.
And then you also have Hessians. And generally, everything is written in JAX and made to be a JAX object. So actually, you can basically call gradient on anything you can imagine within our library. It's just we focus on the aspect of differentiating through the system dynamics.
Sounds good. So I have a question on the body dynamics paper. It should be for Dan, I guess. Did you try and compare with open source projects like OpenPose on your work?
Yeah, so we haven't yet compared ourselves with things like OpenPose or like forward simulators like OpenSim. We did compare ourselves with different tracking algorithms that have some, spatial and temporal constraints. But the thing we cared about most isn't just the quality of the reconstruction or the simulation, but actually the identity of the physical quantities in any moment in time. We wanted to get the inertia and to get the fictitious forces and get this whole inverse dynamics quantities. So I wasn't aware that another method can accurately infer these from noisy joint positions. But yeah, I'll be happy to learn more about that.
Thanks. I think the next question is on the HDR paper. Is that Jung Hee?
Yeah.
So what sampling strategy do you use for sampling pixels, and can this method be improved somehow?
Yeah. For sampling, we use Grossberg sampling method for getting the pixel values from the multi-exposure stack. And I guess there can be more efficient or way to get the samples, but because we gather all the values for 0 to 255, so I don't think other methods could much improve the total HDR consumption structure performance. Yeah.
Sounds good. Yeah. So we have a question on the blend shape paper, and this: how do you actually choose facial landmarks, and will a poor choice of landmarks impact the output? Have you assessed some of that?
So first question, how we choose the landmark? There is the FACS system. So we manually decide the landmarks on the blend shape according to the FACS system definition of the landmarks. And for the second question, can you please repeat?
Yeah, it's about do a poor choice of landmarks impact your output a lot? Do the landmarks have to be very carefully handcrafted, or I think what it means is if you chose something else, would your results vary drastically?
Okay. Yeah. So because originally the blend shape can be considered as the dense mesh that can accurately capture every detail of the facial muscle of the deformation of the facial skin. But in our workshop, in our current work, we just use the landmarks to measure the deformation of the geometry. If we use other measurements, or if we directly use the whole dense mesh, there will be more accurate, these are the more accurate measurements of the deformation. So we expect the improvement of the performance of our top-down model if we use this dense mesh or other measurements instead of the landmarks.
Yeah, sounds great. Thanks. I have another question, I think, on body dynamics. This is great work. Can you give us an idea of the types of problems that this might be applied in? The mouse model seems quite useful.
Yeah, so this whole statistical kind of mechanical project came about through the actual neuroscience application. So our collaborators from the Costa Lab at Columbia, they're recording from the motor cortex of a mouse while it's performing some sort of reinforcement task. It's controlling the joystick, and they're recording from several populations within the motor cortex. And one question that arose was, what is actually the mechanical quantities that are being controlled and tracked by these motor and neurons? So imagine that in addition to the stuff that I've shown you here, we have time series of, say, of neurons in different brain regions, and we would like to regress them with these mechanical quantities and say, well, this population cares about the end effector pose, sort of a high level representation of behavior. Where do I want to go as an agent? And another population may control the torques and the low level sort of muscle commands. So it's a description of like biological motor control.
That sounds very cool. And yeah, it's a new dimension to this workshop altogether. So in the interest of time, I'll just take one more last question. And yeah, of course, I guess you'll have a lot of opportunity to chat about in the poster session as well. So this one's for Paula, like about DeLuca. Do you plan on extending the suite of simulations to other physical phenomena like soft robots or fluids? I guess there's just about next steps.
Yes, yeah. So that's our main plan, to basically extend to more sophisticated simulation environments. I think for the beginning, we'll still focus on tasks that are fully that we expect to be that are differentiable inherently. But then the plan is to evolve and maybe even consider harder setups.
Sounds great. So yeah, with this, I'd like to thank all of you for joining in and for taking time to answer questions.